It's about time. 1 more minute at most. How close are you? Oh, that's really bad. Can you put it on it? It'll help some. Test.
Isn't it due a week before or 3 days before? So yeah, there's an ops department, so what's the rule for that? Math is 2 weeks before. 2 weeks before.
You're gonna get started?
Biraj says that he wants to do some opening remarks.
Oh, wait 2 minutes.
Exactly. So right to the minute.
You should not start. No, you should not start early.
How's the? Did you hear back from the?
Thanks.
Thank you. So, I'm supposed to starting in July 1st, which is why I'm rushing.
Actually, I should just complete it.
Congratulations.
I was very worried that even when I can't be off. And I'm so scared that somehow think. Oh, community. Yeah, thank you so much.
Yeah, I think hopefully the offer you'll be okay. Some of our schools, I know graduate schools are all the same offers. I think like.
And then also there are a lot of departments that just send out less offers.
Yeah, once you got one, it's good.
Thank you.
What? Yeah. You're the one who would standard quality.
No, I know that's me.
That makes you up for the other.
Yeah, we just wrote. Yeah,
Just
you can tell.
Okay, I guess I can start it. Thanks everyone for coming. This is the first Atlanta SIAM student conference. We got Georgia Tech, Emory, and Georgia State University. I mean, it's all in Atlanta, but I think in the future, potentially we could invite other schools. I don't know what schools are like nearby, but definitely these three, there's a lot of graduate students here. And I think this is a great opportunity that we should continue doing going forward. So we're starting with a coding workshop by Carter. Then we're gonna get some refreshments. Then we have a bunch of talks, and then we have posters. So yeah, let's get started.
All right. So I'm a PhD student in math at Georgia State. I think I started, 2022? Okay. So I'm close to the end. Forgotten when I started it. But I work in the Shilnikov Neurodynamical Systems Lab, and we do a bunch of computational stuff. And before I came, we used a lot of MATLAB. And me and my lab mate, Jack, we're kind of experienced with Julia. And so we switched over to that, and we found that it's made it easier for us to keep maintainable code. The code runs faster. We can run it on GPUs without any issues. So I'm just showing off like how to get performant and kind of extensible modular Julia code today. And some of the libraries that we use for dynamical systems, because the ecosystems in Julia are not that well documented. And a lot of times you actually have to go and talk to the developers themselves on Slack if you want any information about it, because they don't write a lot of documentation. A lot of it's fairly new. Let's see. So just to get started, if you don't have Julia installed, that's okay. Like, you don't have to follow along if you don't want to, but if you do want to, you can go to Colab. So this URL right here, the base URL, colab.research.google.com. And normally it starts up in Python, so you have to go here to the runtime type and switch to Julia. This is new. It wasn't here, I think, a year ago even. So they just added this. And then you just click connect, and then you can run Julia code. So the benefit of Julia is it's as easy to write as Python or MATLAB, and it can be made as fast as C in most cases. But you will find when you start using Julia, let's see. Let me turn, that's fine. We'll just keep the explosions on. That when you start using it, it might feel kind of sluggish. And it used to be really bad. Like if you wanted to import a package, it used to take up to 50 minutes sometimes to get it to import. But they've improved this a lot in the last couple of years. So I'm going to install a package, and we'll do ordinary diff EQ.
How do you change to Julia?
So over here, you should have a connect button. Don't click that. Click on this drop down beside it, and then go to change runtime type, and then pick Julia from runtime types. Yep.
I see. Thank you so much.
Mm-hmm. And then you have to click connect, or you can just run one of these code blocks, and it'll automatically connect to a runtime. So here it installs all the dependencies, and takes a little while. And then when you go to actually import, you use using. This still is installing. But you have to do this every time you want to run a Colab notebook. So it's kind of annoying, actually.
Can you show the first line? Okay.
The first one? Yeah. But it'll take a while because Julia is compiled. It's JIT compiled. So every time you import anything, it has to compile the entire library and all its dependencies. And then it caches everything after. So the next time you do it, you don't have to precompile again. But if you update,
Thank you.
if you update a package, you have to precompile again, and sometimes it can take 20 minutes. So you kind of learn to do like all your installations that you need the night of before you go in to work on something new. But once you get them installed, it's fast. Let's see. So you get the point. It's going to take a minute. So I've actually got some prepared notebooks. So here on GitHub, you can get all the source code for the workshop. And it's in notebooks. And there's just 3 of them here. So manifest and project are config files for this repository. And they store information about dependencies, versions, all these sorts of things. And then these 3 are the notebooks that we're going to look at. So type system is the first, and you can actually see an unexecuted version of it in GitHub. But we'll go over that right next. But yeah, the point of this is using ordinary diffeq is going to take like a minute or 2 to actually do the first time. And that's literally just importing the library. It's because you're compiling. Okay. So you can run these notebooks in Colab, but you'll have to manually install packages. So wherever I do, let's go to a different one. I don't think this has dependencies. Whenever I run something like this, you would actually have to go here and do this using package and then package.add glmakey and then run it. And then you can delete this after you do that one time because it'll be installed in your local config. Okay. But I've already installed everything locally, and if you do this locally, manifest and project will take care of it for you, so you don't have to do anything. Okay. So the big thing with performance in Julia is it's compiled, and you have static typing. So you need to make sure that the compiler has enough information about the types that you're using in your code so that it can do the optimizations it needs to. It does have like duck typing like Python or like TypeScript or something. So you can just not specify types. So if you want to write a quick script, you don't have to put any type in annotations or anything, and it'll just work. But if you want to optimize it, you can restrict to more concrete types or something that are more suited to what you're doing. Like you can restrict to float 16s if you're doing GPU computations to make it really fast. You can use like int 8, so 8-bit integers, whatever you want. And you can manually specify all that after the fact to improve performance. But there are kind of 5 main things that will improve performance and let you write really modular code and extend libraries and all this nice stuff that Julia is good for. So the first one is, let's see, interfaces and abstract types. But I've got this table here as a reference. So sometimes I kind of forget what these are, or like what type operators there are. So it's nice to just have one table that shows kind of everything. So you can assert the type of something. Let's see. By doing maybe let's do this. My array equals, and then I'm going to make a vector, and then I can do 2, 3, 4, and then I'll check the type of this array. So this is a vector of int 64s. But instead, if I want to make these be floats, I can put a type annotation here on the array, or on the vector literal, and it will automatically promote everything to float 64s. You can also do this on the actual literals themselves. You can, of course, just change them to floats with decimal notation, or I think you can do this. And so the vector type accepts this parameter, and I think it's going to promote everything. So if I make 2 be a float, it's going to want me to enforce for each of them. Oh. All right, so it doesn't like that. So I should do it with 0.0. So then I don't have to actually do the coercion here. But if I wanted to make a variable and I wanted to restrict it to be a certain type, I can just do like myvar and then put what the type I want it to be is. So in like functions, when you specify the parameters for a function, you can do this to annotate them. Okay. All right. And then there's all these other operators, and we'll see using them here in a second. So you might be familiar with like object-oriented programming or something. So you specify like some class or something, and it's supposed to contain data and then operations on that data. Julia does not have classes. It has structs like C. So I think I create a struct down here somewhere. Yep, a sparse matrix. But it just contains data. You don't actually contain any of the, you don't write any of the functionality, the methods into the data types. In Julia, you specify them externally. So it follows kind of this anemic domain model. It's more like Rust or Haskell or something than it is like C++ or Java. So interfaces are, if you have some types that are different types, but they should all have some kind of common functionality. Interfaces are what people talk about for specifying what common functionality these different types should have. But they're not actually a language feature. So people will talk about them, but you should understand that they're not like an actual like keyword thing you can specify in Julia. Instead, you have something called abstract types. And so you create abstract types, like you can make a person abstract type, and then you might have a man and a woman, or like child or something, like a concrete type that implements that abstract type. So down here are some examples of actually how the number types are specified in Julia. So they literally just write abstract type number, and there's no more information. And that is how it's implemented in the core of Julia. That's all they have to do. And then you can subtype them, the other types. So real is a subtype of number. So any function that wants a number will accept a real number, or an abstract float, or an integer, or anything like this. And then like int64 would be a concrete type that implements integer. So yeah, you can specify your arguments have to have particular types, like abstract types they want to implement. And then you can define these functions on the abstract types and implement the interfaces that you want. And there's this nice reference here about interfaces. And it shows some of the common interfaces, like everything, no matter what, has to implement this iterate function. And then for certain things like vector-like objects or types, They have to implement particular things. And there's not an abstract type associated to that necessarily. So there's some nice reference here on like what people expect when they're using your code. Oops. Okay. Let's see. So yeah, -7 is an int64, so you can supply that for a number, and it works. And then the return type is int64s as well for that, and you just get 42, so you don't have to do anything about making the actual type that you put in be an argument. Okay. So subtyping is nice because it lets us implement these abstract types as concrete types. So I make a new concrete type here called 0, and it's just an empty struct. So that's generally how you specify a concrete type. And it implements numbers, so it's a subtype of that. And then I define some of the basic arithmetic interface methods that they're expecting from the base package. So addition, subtraction, multiplication, division. And I allow those within 0. So I can subtract a 0 and a 0, or I can do it with a number and a 0. So anything that implements that, I can combine with this new 0 concrete type. And then show is just like if I print out, or if I want a string representation of a 0, it will produce this 0 string in the console. So here we do some operations. I make I instantiate the 0 struct, and 3 of them work. So I get what I expect, add 0 to 0, I get another 0 of 0 type, not like the number 0 as an integer or something. And then this works well, this works well. And then I try to divide by 0, and up here when I define division, I enforce that it has to throw an arrow. So you need to implement all this stuff manually. Okay. So next thing is parametric types. So oftentimes you'll have container types, like you'll have an array or a matrix or something, and then the array or matrix may be a different type. It might be a sparse matrix. It might be just a regular matrix. It might be like an infinite matrix or an infinite sparse matrix. So it would have like infinitely many rows or columns and only finitely many non-zero values or something, entries. So you want different types for the container type as well as for the contained like element type. So you have a way to specify restrictions on what the contained type is supposed to be. Also, the collab just finished, so you can see how long that takes. So this notation here with the curly braces is how you do parametric types. So I'm just saying here, I'm making a sparse matrix concrete type. And whenever I make a sparse matrix, I need to specify what the type of the entries is going to be. And then sparse matrix is going to be a subtype of abstract matrix. And I'm only implementing this for number entries. So here's some things you need to define for sparse matrices. You need to define the size, what indices the non-zero values lie at, and then what the values at those non-zero entries are. And then you have these predefined types like tuple, vector, that are parametric types. So you just take whatever T was, like it binds the type to T, and then you can use it in the struct's definition. So we just implement a constructor, ways to do indexing. Let's see, updating the entries at particular indices. And then like if you set it to 0, it should delete it from the index and value properties of the struct. And then addition, multiplication, and then multiplication with scalars, both ways, on the left and on the right, and then a show operation, and that's all. I could write like multiplication addition with sparse matrices and regular matrices, but just be like 3 times as long because I have to do left and right. And then we create 2 sparse matrices, which have random entries in the first 10 rows and columns and they're both, one's a 50 by 7, the other's a 7 by 50, and then I multiply them. So I get a result, which is a 50 by 50. And now we can show what they look like. So this is how the show function was implemented for sparse matrices. So it doesn't print out the matrix because it might be really big. And this is just a simple way to show what row, column you're on and what the value is if it's not 0. And then the result of the multiplication is this. So I get a 50 by 50, and these are all the non-zero entries. Something seems funny about the, so it's not the first, and it's like 10 non-zero entries, and then they're at random indices. Okay, so that's it for parametric types. There's not really any more to that. You just create super types and subtypes of particular other types for your parameters. Let's see. And, there's one more thing. So when you implement a method, you will have this type parameter. And so that's for the entries in the sparse matrix that you're accepting as an argument. And you have to specify, sometimes you'll want to specify constraints on that. And you won't actually put it in here. Like you'll say that as your subtype number. Well, you actually have to put it in a where clause outside. And I could restrict this further, so I could implement a particular kind of multiplication just on the 0 type or something. So I could actually say, like, I could change this to like this. Or you can even do this. And then remove the where clause, because I don't have any types, type parameters that I'm binding to, or type variables, I think they call it. But yeah, in any function that has these type variables, you can specify restrictions out here in a where clause. Okay. So that's it for parametric types. Multiple dispatch is kind of like the main thing in Julia that's different from every other language, and it was a decision at the very start of creating Julia. And it allows you to do a lot of nice stuff with making code very modular. It lets you extend other people's libraries without actually having to go in and change their code. And it lets you get good performance from compiler optimization without too much work. So the idea is, like in Python, if you have a class and then you implement a method in that class, the method, when you call the function, it has self as a parameter for the method, as the first parameter. And so you can think of the method as not being a method of that class, but just a general function. And then you can have two methods that have the same name, but like if I do, let's see, where's my code block? So you can do like class, my class, and then you'll like do a particular function or a method, my method, and then you have to put this, and then some other stuff, some other variables, and then pass, just to not do anything because I don't want to implement it. And then when you call this, you'll do my object equals my class, and you want to call the method now, so you'll do my object dot my method, and then you don't have to put anything for the self argument, and then you'll put some kind of like particular values in for A and B. But you can think of this as it's stubbing in as my object in for the self parameter, and then you're just actually calling this my method. But you might have two classes that have the same method name. So it picks which my method to use if I have two such classes based on what is stubbed in for the self parameter. So this is single dispatch. It picks what function out of all the ones with the same name based on the first parameter. Let's see. In C++ Java, you can actually make two functions that have the same name, but which one gets called depends on the types of the arguments. But the compiler has to like unroll all this stuff and give them like different names, so to speak, like different memory addresses in the compiled code at compile time. So you can't do like inference at at runtime on what types you're using. So you'll have like ambiguities in what function is supposed to be getting called if it's not totally clear to the compiler. And then duck typing lets you actually at runtime check the types of the arguments that you're supplying to a function and then do different operations based on what the types are. So you can actually look up the type of a variable that's supplied. You'll have one function with a particular name. You can't do overloading, but you can then look at the types and do if-elses just to pick what like set of functionality you want to implement for those types. So multiple dispatch lets you match against all the types, and it works at compile time, but it also allows you to do something kind of like duck typing, where you are able, so the specifics aren't too important about like what's going on with the compiler. I mean, you could read about this, but like as far as actually using multiple dispatch, you write functions, you can have 3 with the same name, and then as long as they have different argument types, you can be sure that whenever you call the function with particular values for your arguments, it's going to match against those, and it's going to be resolved at compile time. So it has like a lookup table in the compiled code, and you don't have to worry about performance penalties for doing this like you would with duck typing. And it's a little cleaner to read because you don't just have one function with all the possible types. So let's see. Just it improves performance. It lets you do like SIMD vectorization. So SIMD is just like if you have a vector like, and you're doing an operation in every element of the vector, you might write machine code that operates one by one on them, or you can like write machine code if you're writing handwritten assembly or something that like puts them all 2 of them in a register and then does a single operation on them with like bit masking or something like that. So Julia is able to do that with the JIT compiler, and you can kind of guide it with these 2 macros. So the one thing to look out for with multiple dispatch is if you come up with an ambiguity in your parameter types, the compiler may not be able to resolve it. So it's going to try to match against the most concrete type for each argument. So here I have got this example. This should not have.
You might have the other method in state still.
I already ran this. I didn't run this, did I? Let's see. I can just restart the runtime. I didn't using anything, so I should be able to just run it again. Why is it freezing like that? Okay. Okay. So this works, and I'm just saying, okay, we've got A is an abstract vector of any type that is a subtype of number. B is a vector, so that is a concrete type that actually implements or subtypes abstract vector. And the return type should be a vector. So it's going to promote whatever this is to a vector, hopefully. And I just added the 2 vectors, element by element. And I'm assuming the length is the same, so that should work, and it does work. And then I can check all the methods with this name, add vectors. And there should just be 1. And it tells me what the types of the parameters are. If I implement 2 of these, let's see, let me comment this one out so I don't get an error the first time. And then I should have 2. So vector, abstract vector, and then abstract vector, vector. And they do the same thing. This just swaps the arguments and then calls the element. But if I actually try to use this, now it's saying, well, this is a vector of int64s, and this is a vector of int64s. So it's going to match against the implementation with the concrete types, or the closest types to the concrete types in the hierarchy. And these, there's no, like they're incomparable. And you have to actually be comparable across each element. So if there's even a single ambiguity in one argument, it's going to panic. All right, so I get a method error, and it tells me that there's a ambiguity here. But yeah, I mean, you can define them, you just can't call them. So that is the only thing to look out for. Just make sure that you don't have ambiguities. And you can make two functions with the same name return different things. So not only can the arguments differ in type, so I can supply a string and it should return a string, or I can supply an integer and it should return an int. But you can't match on the return types. So this worked because I didn't call the second one, or the first one. So here it's going to throw a type error because I'm trying to coerce to this. And the reason why that's happening is if we look at the bottom, it should be showing the methods. Well, there's only one return something. So I defined two and they have different type signatures. So what's happening? Well, this one is the only one getting used because I'm actually defining this, and then the Julia compiler sees that this gets defined and it kind of clashes with this, and it's just going to throw out the first one and let you redefine it. So this doesn't even exist anymore by the end of the code. So that's why this throws an error, because I am trying to coerce the result of this, which should be an int, into a string, and it doesn't like that. I could just convert it to a string manually with the show method or like some stringifier method, but beside the point. All right, so the big thing when you're actually writing code for performance is type stability. So let's see. There's a bunch of libraries for doing profiling and checking type stability and getting nice debug error messages or like information about what the type stability is. So these are some of those. But you don't really need them. You can just use the built-in macro code warn type, and it'll show you all the information about the stability of the types. So stability of the type is the compiler should be able to infer what the concrete types are as you call a function, even if you don't specify them in type annotations for the function. So I've got two implementations for this function. One, they do the same thing, but let's see, they should both return float 64s because I'm adding these floats. This will promote I to a float, even though it starts as an integer. And by the end, once we've added a bunch of floats, they'll be promoting S to a float, so we should be returning a float. And in this case, everything's a float except I, and that just gets promoted at each step, so that's fine. So let's run that and check the type stability. Okay. So here the issue is S is the compiler's not able to figure out whether S should be a float or int. So the reason is that we defined it initially to be an int, and depending on how many times this loop runs, because the compiler doesn't know, we may end up having to return an int or a float. But in this one, it starts as a float, and we never demote it to an int. So it's not ambiguous anymore. So I shouldn't have issues there. All right. So you're looking for these yellow messages. So S is a union of float 64 and N64. So this one's fine. This is just some internal thing, and having unions of nothing and something else is okay. But actually, we're going to have a pretty big performance penalty for having this type ambiguity. And that doesn't happen in the stable implementation, right? So that's inferred to be a float 64. And then using the tests package, you can actually check the return types and see if they're inferred to be concrete. And the unstable one isn't able to do so because it can't infer the concrete type, and then stable sum is able to infer it, and it just prints out what the result is. So let's see what the performance is for each of these. So this is for the unstable, and this is for the stable. They do exactly the same thing, same argument being supplied. And what is this, like a 4.5 times speed up? Pretty good. And you can keep running it, and you should have different run times each time. 4 times speed up. A little over 2. So helps a lot.
Sorry.
Yes.
So the main idea why one is faster than the other one is because when you have the things correctly defined, upper compile the code, assign the variables, and it just runs it. And when it's not correctly defined, every time it figures it out, or what is happening that makes the time different?
So it's having to do if else in the compiled code if it's not inferred. You can actually check the way it compiles. I haven't looked at this much, so I might not be able to interpret what it spits out, but you can use this macro, and it should be unstable some like 10 or something. Let's see. Okay, so using LVM, I have to add it. Hopefully it doesn't take but more than like a couple seconds. But yeah, it's going to compile 2 routes, so to speak, and then it's going to have to check at each step which one to run, and that's going to incur a really big penalty compared to just adding a number.
This is something that Python natively doesn't have. Python just does this every time, right?
Python does do this every time. I think PyPy or like Numba or something might be able to do some stuff like this. But yeah, the C Python can.
Python version that has you can code like in C, right?
You can use C types,
Yes.
and you should be able to. I don't know exactly how granular the control is for that, but here you can actually check the LLVM intermediate representation. I'm not going to sit here and try to interpret the assembly, but if you're interested in that, people do it. If you're posting, if you're trying to do benchmarks and profiling and performance improvements, and you go like post an issue on somebody's packages, GitHub or something, a lot of times they'll want this. So just knowing about like this macro is useful. You can actually inspect the compiled result. But yeah, just literally just abuse this code one type macro anytime you're not getting the performance you want, and it's really helpful. A lot of the times when I'm doing like parameter sweeps for dynamical systems, I'll accidentally introduce a type instability and it'll just like completely wreck the performance. I'll get like 100 times the time that I should expect. It's terrible. So just going through and checking the type stability is the quickest, like biggest way to improve the performance. It's the first thing you check. So that's everything about the type system. Hopefully, let's keep blocking. Hopefully that's all straightforward. I don't know what just happened, but yeah, up here at the top is a table, and this is in GitHub again, if you ever want to play with this or refer back to it. So this is the repository. Okay. So that's all I wanted to talk about for just basic Julia. And there are a lot of packages in Julia, so let me take a look at a couple of them. I got into Julia in 2019 because I don't know if you guys have heard of like AlphaGo, but after AlphaGo, there was another model called MuZero. And the thing, let's see, I've actually got a picture here of what I want to describe. So here's the poster that DeepMind did for that model. And I knew Python for a long time and had like written neural networks with PyTorch and stuff. But the thing is, like, PyTorch computes this or precompiles this computational graph, and all the inference code is written in C++. So it's able to do really fast computations. And you can do like backpropagation, like auto diff, all this stuff really quick. So you don't have to worry about the slowness of Python when you're doing neural networks or anything. But if you are combining like PyTorch neural networks with some kind of like Monte Carlo tree search like they do here, which is like, let's say you're playing Go, you look at a board state, you can check, like AlphaGo check 3 things. It would compute a probability distribution for professional players over all the possible moves in the current state. And it would just say, okay, a professional is likely to play like the 3-3 point or something. And so that's the action head or the policy head. You had a value head, which was supposed to predict, given the current state, what the likelihood of win rate, so a percentage win for black and white was. And then you had another one, which was supposed to be predicting, it's another value head. It was predicting the most likely score for each player at the end. And win condition is just like, do you have a higher score than the other person at the end of the game? So that's not enough because, I mean, it's really hard to get a neural network to play this game just from looking at the current board state. And you need to actually do rollouts and check like what the possible playouts are. So they implemented this thing called Monte Carlo tree search, where they do the inference, they get the policy head to spit out the most likely moves, it samples that probability distribution, and does this repeatedly. So you're doing Monte Carlo rollouts. And you'll play each move, you'll simulate the after state, you'll simulate the other player's move through just, again, doing a sampling of the probability distribution for policy head. And then you just keep doing this, and then you play till the end of the game or to some state that you're able to get higher certainties about the results for the win probability. And then you update the win probability for the different moves, after states, using this Monte Carlo tree search, and then you sample according to whatever maximizes the win probability. So doing this rollout is not something the neural network is doing, and you're doing a lot of iterations really fast. So Python is not able to encode this in the computational graph for TensorFlow or PyTorch or anything. So you actually have to do this with iteration in Python with a for loop or something, and it's slow. So somebody implemented this in Julia after the fact, and I saw this and I was like, hey, this is pretty cool. I want to like try doing reinforcement learning. So I tried it, and I found it pretty nice to use. It wasn't hard. I didn't know all this stuff about type systems back then, so kind of stuck. But it's kind of ironic because like nobody really uses Julia for machine learning now, since like we're really only doing inference, and we're not doing like this rollout stuff most of the time, like with LLMs or something. So Julia just kind of fell off for that. But there are some like neural network libraries like Flux. This is probably the most popular one. It has like AutoDiff, nice inference stuff. But it caught on in dynamical systems because in general, you're not doing a lot of super large neural networks. And even if you are, you can still use it. It's just that the ecosystem for machine learning is better in Python. Let's see. And you can like write really simple code in Julia too, and then you can optimize it after the fact by adding type annotations, all this stuff. So it's nice and iterative from the development standpoint. Okay. So let's see. Is this the right one? Should be. So we're going to look at 2 dynamical systems. One's going to be an integrate and fire neuron model, and the other one's going to be the Lorenz system. So the 3D, like the butterfly looking thing. It has a strange attractor. And we'll visualize it and see what that looks like and how to actually compute trajectories and stuff. So the reason I wanted to look at the integrate and fire model is because the solutions to it are distributions. So you can't actually use like Euler method or RK4 or anything for that. You use it for the parts that are like the parts of the solutions that are functions, but you have these Dirac deltas where you have sudden jumps once you hit a voltage threshold. So like I'll have some kind of externally supplied current. So this is a voltage and this is time. And if I supply an excitatory current, it's going to move the voltage away from the resting voltage up to wherever it's supposed to go, depending on what the current is. And then once it hits this voltage threshold, it's a parameter for the model. It'll suddenly spike. And then instantly it'll drop back down to some rebound voltage. And in my model, I just treat the resting voltage as the rebound voltage. So simplifies things a little bit. Takes away one parameter. Here's the model. It's just one ODE. And then you have this condition that you need to check at every time step, or higher resolution than every time step, just all time, where you say, okay, am I at the voltage threshold? If so, jump up to the spike voltage for an instant, and then immediately drop back down to the rebound voltage. So I have, this is like a forcing. So it doesn't depend on the current state, and I can specify that forcing current to be whatever I want it to be as a time series, or as a function of time. And then I have this like linear part here. So this is just a number. It's the conductance for the leak channel. And then it's going to just move exponentially. So you're going to have exponential solutions converging to the resting voltage. So first thing you do when you're using the ordinary diff EQ package, right? So this is the one you'll typically use. There's also this. So if you're running a lot of solutions, you can use diff EQ GPU. But also ordinary diff EQ works with CPU multi-threading, so we can actually get parallelization a little bit without using the GPU. And the code for this and the GPU version is essentially the same. Not really any change you need to make. So I could pretty much just switch packages and then maybe change one or two things. Like when I define the ODE problem, I'll have to change one thing. But you define the derivative. So I've done this in place. So I could take away this exclamation point and remove this dV parameter and do out of place derivatives. And it would be a little simpler, but this is faster. So what it's doing is in Julia, if you have this exclamation point, it's saying the first parameter I'm actually going to mutate, and I'm not going to necessarily return it. So I'm going to change it, and then things outside the scope of this function should be able to see the changes. Right? So I'm actually manipulating the memory, wherever this dv is stored in memory. And then these three, I'm not going to mutate them. You can only mutate the first parameter, I believe. I've never seen anybody mutate anything else. But you just put in the state, you put the parameters, and then the time. That's what the derivative function is expecting. All differential equations need to be specified this way. So I extract the parameters from the P vector. So I have capacitance, the leak conductance, the rest voltage, and then I've got two more, which are like the action potential, max voltage, and then the, what is that? What is that? Oh, this one's the threshold voltage, and that's the action potential max. And then I just mutate dV, so it's going to be a vector of the same dimension as V is. So as many state variables as I've got, the derivative should have. So it's going to be dV dt is the first entry here, and I just want to set that to whatever the derivative should be, and that's coming from the formula above. Yes?
Sorry, I would understand the idea of the mutation.
Yeah, so let me just, it's really easy to just show you. So if I copy this down here, I remove this, so I'm not going to do the mutation anymore. So I took away the exclamation point. I take away the first parameter. And then instead of just mutating this and assuming dV already exists, because I haven't bound that variable name to anything yet, I do this. I just make I allocate a new vector, and then I can return that. And actually, I literally can just do this, and it just automatically returns. You can write return, but you don't have to. So this would be the out of place implementation. It works exactly the same. It's just a little slower.
It's just purely a matter of speed.
Yes.
Okay, thank you.
Okay, so let's run that. All right, so we've got our derivatives defined. Now I need some way to handle the threshold events, right? So I need to actually capture the action potentials. And if I just continued solving the linear ODE at the action potentials, and I just wanted to store some details about the time that the action potential occurred, I would not need some of this functionality that I'm about to show, but you actually do mutate the state. Like when you get here, you reset the state for the ODE back down to the rebound voltage. So we'll have to do that. And this is like one of the more powerful things in the ordinary differential equations library. So we use this a ton. You can do arbitrarily complicated calculations in here. We use this for symbolic dynamics a lot. We'll run long, really, really long trajectories in parallel, and we won't save the trajectories. So they, there's too much to store in memory. But instead, we're going to do symbolic encoding on the fly. And you can do that encoding and store it in a vector for each trajectory that you're running. And then you can just throw away the solution trajectory and not even store it. And then you'll be able to access whatever the symbolic encodings were after the fact. So like I could just not even store the trajectory for this integrate and fire model and literally just store the times of the action potentials, and it would be much more memory efficient. Only a few bytes instead of however many it takes to store the trajectory. So what you do is I'm going to actually store the action potential times. So I make a vector for that. And then you have to define two things. You need a condition and an affect. So the condition is going to run at every time step in the integrator. And it's going to eat the state and the time and this integrator object, which contains things like the parameters at the current time. So you can actually mutate the parameters throughout the trajectory. You can store arbitrary things in the parameter vector, so it's a little weird. Like they have some examples online, but like I could store like an image that I'm updating live during the integration in this parameter vector that has nothing to do with the differential equation. So I could also store AP times in there and then just update that. So you can mutate that way. And that used to be the way people would do this, but they've improved it. So you can just specify things externally to the condition. So I grab the parameters, vrest and vth. I want to check if I'm at the threshold voltage. I don't need this vrest. That's actually irrelevant. So I need the threshold voltage, and I am going to return a value that when it hits 0, it should trigger an event. So I want to check if I'm at the threshold voltage. So I'm just going to check, is the voltage equal to the threshold voltage? If so, it's 0. And if I flipped it around so I like made this negative, it would not work anymore because I'm going to specify that I only want to check for conditions where I'm crossing the threshold voltage from below to above. So you can specify that as extra constraint. So the condition is just doing this. Now, this has arbitrary precision. It does a reparameterization at the event detection. So because I'm going to use what's called a continuous callback, it's going to look at 2 points in time where the solution satisfies the condition being 0, or less than 0 on one side, and then greater than 0 on the other side. And then it's going to reparameterize by the arc length, I believe, and then figure out the exact point at which the event was supposed to occur by doing some extra integration. So continuous callback gives you arbitrary time precision, even though I might have a large time step for the integrator. Okay. So the affect is when you actually trigger the event specified by the condition. Affect is called. And we're just going to grab the resting voltage because we're going to reset the state to the resting voltage when this event's detected. And then we're going to push the integrator time to the action potential times when this happens. And then you create a continuous callback. You specify the condition and the affect. And then I say affect neg is nothing. So I don't want to detect over under crossings for the threshold voltage. Okay. Now, I've left one thing out. I didn't define this function, the external current. Because Julia does 2-pass compilation, it's going to not have issues with this. Like it'll run one generation of something like an AST, and it's going to figure out. It's basically like running a C header file or something. It's going to figure out what all the methods are supposed to be, and then it's going to go and actually compile everything on the second run through, and it'll know what functions haven't been defined yet when you're calling them. So you can do this. Otherwise, I'd have to put IEXT above wherever it gets used. So I can define that now. And I've got 3 examples. I can specify an amplitude and a period. So I'm going to have periodic forcing. This one is just kind of sinusoidal forcing with some deformations. And we'll plot that and see what it looks like. Lost my computer again. Okay. There we go. It's not my computer. I don't know what. These other programs work. It's just VS Code. Okay. So I ran that. Now I'm going to specify parameters. So I pick a capacitance, conductance, these 3 guys, and then I put a time span for the integration. So I need to say how long I want to integrate for. You can also integrate for really long times, like unreasonably long, that would take like 1,000,000 years, and then just have a terminal condition specified in the condition for your callback. So that works. We use that for generating Poincare recurrence plots a lot of times, or not Poincare return maps, because you don't know how long the integration is going to take to get back to the surfaces section. And you don't want to do extra integration. So specify an initial condition, and I just start with the resting voltage as my initial voltage. And I reinitialize the AP times vector. You don't have to do this, but I just did it because I want to reset if I want to run this block again. And then do a solve. So you specify an ODE problem, you provide the derivatives, and then you provide the initial conditions and the time span and the parameters, and that's all you have to do. And then once the ODE problem is defined as prop, you can compute the solution. You specify an integrator. So this is a modified Runge-Kutta 4 method. And then you specify some tolerances. So this is actually an adaptive method. And then you have to say what the callback is supposed to be, which was that callback, the continuous callback based on the condition and the affect that are defined for the spikes. So I get a solution object, and it prints out the times for the trajectories, sampled points. I can modify that in the solve call with extra keyword arguments. And then it also gives me the states. So this is my voltage time series. All right. So GL Makey for plotting. So GL Makey is like this set of plotting libraries that's interactive and really nice. We use it for all our publications. So it's kind of like configurable enough that you can make publication quality figures. And you can also make interactive tools that are really nice. And GL is the one that runs on the graphics card, so it's really fast. There's also a web GL Makey that runs in the web browser. And there's a Cairo Makey that just produces static plots on the CPU. So here's the solution. So you can see it's just these exponential solutions with forcing. Up is excitatory, so it's pushing it upward towards the threshold voltage. And then when I actually hit that threshold voltage, it's going to spike. And then it'll reset back to the resting voltage. And I should have AP times, my vector should have the times of all these red dots. And just to show GL Makey, you can resize and it automatically fixes the aspect ratio. You can move around. It links the plots, ranges together. Really nice. Okay. So that's it for the integrate and fire neuron model for Lorenz. So here's the ODEs for Lorenz. It's 3D. So we're going to need 3D plotting. And we're also going to do a little bifurcation continuation with it. So we should be able to find a Hoff bifurcation and then continue periodic orbit a little bit. And I start with the usual parameter values where you have a strain detractor. So let's define the derivatives. Same old thing, I'm doing it in place. So I'm mutating the derivative vector. It's provided to me by the solver, or the integrator. I set up the integration, which means put your parameters, your initial condition, and your time span, and then compute the trajectory. Same solver. It doesn't like something here. It says larger max iters is needed. So maybe if I cut that trajectory short, it might not have that instability where the tolerances can't be met. Okay, so that solved that. And now we can plot using GeoMakey. So I need to take the, let's see, what did I do? So I look at solution.u, and that's going to be this vector of the vectors, which are my x, y, and z coordinates. I extract them into their own vectors for each coordinate. And then I plot those with lines, create a figure, create an axis in the figure, put the labels, and then just plot the lines and then display the figure. Simple. So it's nice and interactive. I can plot other things on top. I can make things like sliders in this where I can maybe deform the solution. I can only show part of the solution by making a slider. I can make things clickable. So I can select objects in the plot. It's a lot of nice stuff. Okay. So let's look at the bifurcation continuation stuff. So bifurcation kit is, if any of you have used like MatComp before, you can do bifurcation continuation with that, and it's like this graphical user interface. But it only works for small systems of ODEs, like maybe 10 or something. And if you have like several thousand ODEs, it's not going to work because you're having to do these test function computations to do the continuation. And then you're doing like a Newton solver to do a predictor corrective method for finding the next point in the continuation in the parameter space. So it's tough to do for these big systems because you're computing eigenvalues with these test functions all the time. And bifurcation kit is really nice because it has these Krylov subspace methods for the eigenvalue solvers. So the test functions are really fast. And they're intended for large systems. So we put an initial guess for the equilibrium point. And just to like get a sense of like how you can check for like where an equilibrium point is, you can do it in Julia using a Newton solver, or like I've written this app in TypeScript where it's like this website and you can just go to it and then you can just find the equilibrium yourself. And so I can put like, it defaults to Lorenz, so I don't have to put the system in. And then I put an initial guess for where I might want to see if there's an equilibrium somewhere nearby, solve, and it gives me these XYZ coordinates. I can look at where it is. So it's like there should be a saddle focus. And you can look at the eigenvalues for it and the eigenvectors. And then plot like this. And this also does a little bit of bifurcation continuation, but it doesn't work for large systems, and it doesn't do like periodic orbit continuations or anything. But yeah, this is the equilibrium we're looking at. So I just take those XYZ coordinates and I put it into bifurcation kit, and it should be able to figure out where the point is from that. I can perturb it and it should still work, but might as well just put the actual point. Okay. So for bifurcation kit, it wants a different derivative definition. It wants me only to put in the state and the parameters. It does not want an in-place method, though I think you can specify an in-place method. I had some issues with it, and it doesn't want a time, so it wants like a vector field specified autonomously. So it doesn't want there to be any forcing. I don't know if it supports force systems or not, but I didn't see anything about that. So I just do out of place. I allocate the du derivative, and then I just return it. And then I specify this bifurcation problem. I say, okay, put initial state, the parameters, and then I say that I want to do a continuation in the third parameter, which is beta. Okay. So I want to continue that equilibrium in the third parameter. Okay. And then we specify continuation parameters, and I put a range of beta parameter that I want to continue along. So here it spits out some information about the parameters for the continuation. And we can now do the continuation. You can specify like what you want to do here. So like more pin rows, or you can use pseudo arc length continuation. After a few seconds, it gives me the continued curve. Okay, so here it is. This is beta. This is the x coordinate. So the equilibrium is moving up as I increase beta. And there's a hop. So I start here and I go over to here, and along the way there's a hop bifurcation. So I actually get information about that here. And then the endpoint is given to you as well. So any other bifurcations you would see is extra special points. And then I can do a continuation of the Hoff branch if I want to, or I can grab the periodic orbit that comes out of the Hoff and I can continue that. So that's what I did here. I just kind of wanted to see what it looks like in state space. So you just specified the arguments for a periodic orbit continuation, and I want to store what the trajectory is for that periodic orbit at every point along the continuation curve, so I can visualize it after the fact, and put the continuation parameters like the more pin rows, step size. I have to reset my tolerances here, and then I just do the continuation. And I had issues with this one because this periodic orbit grows really slowly, and it is really crazy. So it has a hard time continuing very far. I can only actually get back to the point I started at for the equilibrium continuation. But here it finds a Naimark-Sacker bifurcation, which is where you lose periodicity and you end up like a quasi-periodic orbit on a quasi-periodic orbit on a torus. And so we can plot it then. Okay, so that's right at the Naimark-Sacker. And I can also plot it a little bit after it at the endpoint of the continuation. It just gets too crazy to continue with the mesh size that I'm using for the collocation. So bifurcation kit has three different periodic orbit continuation methods. One's collocation, one is a shooting method, and then the other is I think, trapezoidal method, but collocation is the most precise. And just to kind of see it a little better, I do like a PCA. And plot it in Makey so you can see it a bit better. So it's periodic, but this clearly isn't what it actually looks like. It's just that the precision is insanely small. Like I think 10 to the negative 16 is floating point precision for float 32s. But yeah. it is able to continue a little bit. Okay, so that's it for like bifurcation stuff. So next, I've got an example of parameter sweeps. So there are two libraries we care about. Ordinary diffie-q, so I'm going to do a threaded parameter sweep, and we're going to use chaos tools for computing the Lyapunov spectrum for the Lorentz system. And then we'll do like a heat map plot of the sweep. Again, derivatives, same as before. Parameters, initial condition, time span. Do an integration just to see what we get. Now, the thing about chaos tools, which does our Lyapunov spectrum calculation, is it wants a dynamical system type object supplied instead of the derivatives directly. So I need to specify that it's a coupled ODEs problem. So we do that. We just supply the derivatives. We get a 3D coupled ODEs using TSIT5 by default, some default tolerances. And then I can calculate the Lyapunov spectrum for the initial parameter point, just to see what that looks like. So I should get three numbers. You get one positive, one pretty close to zero, and then one super negative, which you would expect for a 2D attractor. And then we can calculate the Lyapunov dimension. So this is the leading Lyapunov exponent. If it's positive, we're chaotic. If it's zero, we're not. So Lyapunov dimension. And we calculate that to be 2.06 roughly, and it's known to be 2.06 plus or minus 0.01. So the Lyapunov dimension is, if I plot the trajectory again, the attractor is actually a set in state space. So it's the omega limit set of the solutions. So this is a global attractor. Everything gets pulled to it, except like a finite set of points like the equilibria, the three, one down here and then at the center for this alpha foci. But this looks like a two-dimensional thing for the most part. You're not actually seeing the attractor, you're just seeing things really close to it. So it is approximately two-dimensional, but it has fractal dimension if you compute the set. So the Lyapunov dimension is due to this conjecture by Kaplan and York, and it says that the Lyapunov spectrum can actually be used to calculate the fractal dimension. And you get an upper bound, but usually it's tight. But I think it's not a proven conjecture except in certain cases. And I think there are some resolutions where it was shown to be false. And it's hard to get information about this because the paper was really vague that introduced the conjecture. And then I went to look on like Wikipedia and Scholarpedia, and the information on them was wrong and I had to update it. It's not documented well at all, but people use the theorem quite a lot. Like if you ever look at like template theory and chaos topology, they use this idea quite a bit, that you can compute the attractor dimension from the Lyapunov spectrum. So it looks like 2D, but actually the attractor is equivalent to a branch 2 manifold. So it looks like this. So there's this thing called the Berman-Williams projection you can do, and the right side's in front. So it looks like this after the Berman-Williams projection. So this is a branch 2 manifold, and you have along this joining locus, this, or you can think of it as like a one cell or something. The tangent space is singular, so these two have to be tangent to each other when you cross over that joining locus. So it's not exactly a manifold because the tangent space is not well defined, but you can do like a disjoint union of the tangent spaces for the branches, and it makes it possible to formally define what that attractor is as a template. But yeah, nice way to talk about strange attractors. It's template stuff. So that's what the up and up dimension is telling you. It's at the joining locus. How much does that contribute to the fractal dimension of the attractor? Okay. So we compute that to be 0.06 parts of another dimension. So now we can do sweeps. So static arrays is used anytime you're doing parallel stuff. So our conditions, our parameters, everything needs to be a static array when we supply it to the integrator so that we're thread safe. And it improves performance a lot even if you're not doing parallelization. So we redefine our Lorentz derivatives, out of place, static this time. So I make sure it's a static vector. And then I also, for, okay, doing that thing again. For the up and off calculation to be fast, I supply the Jacobians for the Lorentz system. So do that here. And that's, again, static matrix, 3 by 3. And I just hand compute that. You can use finite differencing, but it'll just be slower. And then you specify, again, coupled ODEs, dynamical system, and then supply the Jacobian to a tangent dynamical system. And there's documentation about this in Chaos Tools online. And then I pre-allocate the lambdas vector, and that should be a vector for every parameter value I'm going to sweep over. I specify the ranges up here. I think I skipped over that. But for every parameter value, I should have 3 numbers corresponding to the layup and up exponents. And then I actually compute with multi-threading. So it's really easy to do multi-threading, literally just this macro. You just run it on the for loop, and it spawns off threads for each one. And I am creating a different dynamical system for each thread that I'm going to run. So I check how many threads my processor has available. And it's just going to, within the thread, it's going to mutate this guy. It should be about 1 minute to compute this, I think. After that, I just store the leading layup and up exponents, so access the first of the spectrum for each parameter value. And then the layup and up dimensions, I run the layup and up spectrum through that function that computes this. And sometimes it won't be well defined. So I just put an add in that case. Okay. This is quick. And then I just plot everything. So you get a sweep. If you do this on a GPU, it's going to be much, much faster. But, you know, I can zoom in and stuff and look at everything. So LLEs on the left, the up and up dimension on the right. And I do like a clamping on the up and up dimension. If I didn't do that, you would have an uglier plot. So I just check, is it close to 2 for a minimum? And easy to do these parameter sweeps. And then you can store these vectors, and you don't have to store the trajectories or anything. And then you can make grids more refined and keep doing further computations. But I would say, like, if you're doing parameter sweeps, one big thing to look out for is, like, don't do a big run at the start. Do it like a 10 by 10 grid, and then see how long it's going to take to compute, and then just figure out, like, how much time until the next day you're going to come in. You have to run points, and then just do this thing where you kind of, like, get it working on a small grid, and then compute how many points you'll be able to do by the next day or something. Run that overnight. Because you might run out of memory or something, or you might have like some errors that pop up in runtime that you didn't expect, and Julia's just going to crash. and like you'll come in the next day and you won't have a sweep. So that happens quite a bit. It used to happen a lot more. GeoMakey used to crash a ton of times, and then it would just throw all your data away if you didn't save it. So this doesn't happen anymore, but it used to give us a huge headache. Okay, there's one more little thing I wanted to show really quick. Let's see, let me open this folder. Chaos tools, explore. All right, I did that wrong. Okay. So just a nice kind of interactive program here. So these macros for GeoMakey are really nice because they allow you to do two-way binding with data. So as soon as like a vector's entry or something gets updated, the GeoMakey is going to read it. So you can do things like model view controller designs for GUIs. So it's really nice. A lot of the stuff that like web developers figured out is good for programming these things has been put into the Julia packages. Let's see, almost at the end. Okay. So this is on a 5-dimensional Hodgkin-Huxley model of a neuron. Once it gets going. If it wants to, I don't know why I'm out of memory. There we go. So I've got a few things going on here. I've got a state space where you can see the trajectory updating live. So I'm not storing anything in memory. I'll make that go away. I got a voltage trace, so I'm just extracting one of the 5 dimensions. It is responding. So this is 5-dimensional. I'm projecting it onto 3. And I'll just keep clicking that. But I've got a parameter space here too that I can like pan around and zoom and click on. And live, I can actually click a parameter point, and then it will pick those parameters and let me see what the behavior of the neuron is at that point. So like I've got this pre-computed sweep I did, right? So here's Lyapunov exponents in the red. Here is a conditional block entropy on the spike times, or on spike counts per burst. And so red is like chaotic, blue is non-chaotic. And then this other green thing is a inter-spike interval variance, which allows me to see like how many spikes I'm getting per burst. So here I've got this subthreshold oscillation in this area. And then that's visible. And here I will have a, what kind of bifurcation is this? It's a saddle node of periodic orbits. And then I get 1 spike per burst. So that will happen forever after the first one. And then I can move over here to 2 spikes, 3 spikes, and so on. And then in the windows between, I'll get these chaotic back and forth patterns between like 3 and 4. So let's try that. So 5 spikes, but we haven't converged the attractor yet, unless no, this is 4 and 5. So 4. And then in here, you get like mixed mode oscillations between subthreshold oscillations and burst patterns. And I think Julia updated version, and this has some issues with it now. So I commented out the computation for this, but it actually computes a point array section, like a return map. And you can do things like compute the needing invariance for that return map and compute topological entropy for the dynamical system from that. And all this happens live every time you update the parameter vector using these two-way binding macros and geomakey. So it's really nice. So yeah, you'll spiral outwards, subthreshold oscillations, and then you'll spike once, or you may spike 50 times, who knows. And then here you have tonic spiking behavior. But yeah, this was useful when we were doing a bifurcation continuation for this model, because you need to be able to click around and see what the behavior is everywhere really quickly. So that's why we built this. But yeah, super nice for building interactive tools, and you can just publish them, and then people literally just run the code. They don't have to install anything. It's all handled by the package.toml and the manifest.toml, and it just handles the dependencies for them. So very easy. And I think that is all on my notebooks. So I guess we can take questions.
Yeah, any questions? Okay, well, thanks a lot, Carter. Okay, next we're going to go downstairs to the, what we call the Skiles atrium. It's the common area of Skiles, and that's where we're going to set up coffee and drinks and cookies and donuts. And then we're coming back here at 3 for the talks.